Welcome back, friends. Now, in the last lecture of this series, we are going to look at how to locate a transit stop location. You may remember in the previous lectures, we stopped at understanding how to develop the capacity of various types of stations, and in the other lectures, in the previous lectures other than that, we have also looked at how stations play a very important role. Stations or bus stops play a very important role in a public transportation system, because they are essentially the points from where passengers board or disembark the metro lines or the bus lines or whatever public transportation you have. So, as such, in this lecture what we are going to cover basically is how to determine the location of a bus stop. I mean, we are calling it a bus stop, but most likely you can apply it for a metro stop as well. Maybe you should consider it more of a stop or a station on a rapid transit line. So, if it is a BRTS, bus rapid transit line, then this kind of station location would apply to it. If it is a metro line, it would apply to it. It would not much apply to a regular bus route, but you can adapt this methodology to determine bus stops for a regular bus city bus route as well. So, that is what the topic is going to cover today. Just a quick recap of what are the objectives of a stop or a bus stop or any metro stop or anything. It is to serve the major centers, activity points, and transfer with other lines, right. So, that is a location where everybody needs to access that in a nice in a timely fashion, in a hassle free fashion, so that they can then get on the public transportation system. It has to achieve minimum passenger travel time, right. If you remember, when we looked at the travel time components on a public transportation system, the travel time components consisted of an access time as well as an time that is spent on the transit line. So, but the location of the stations plays an important role in achieving minimum passenger travel time. Then it has to provide maximum area coverage, right. So, if there are a lot of residential complexes around in an area, then the bus stops or the transit stops have to be spaced in such a manner that it is accommodating almost all of those residential areas. It may be also office areas. So, it has to be such that it caters to a majority of them. So, it has to maximize the coverage area, and it has to by doing so it will attract maximum number of passengers and also minimize the system cost. So, there is also a need for not only to look at the demand side of it, right. Demand side looks at how many passengers you can attract, but you should also look at the supply side of it. How many stations can you provide without increasing the cost of operations too much, right. A station will need a lot of infrastructure. A stop will not need so much infrastructure, but would still need some maybe benches, shelters. So, all of this incurs cost. So, how can you have to also look at minimizing the system cost in developing or in locating where the bus stops should be, and also meet other requirements such as economic development, population needs, and so on and so forth. So, these are the overall objectives of locating a stop or a station along the public transportation line. So, if you want to now, for simplicity sake, right, although you have to satisfy all of those objectives that we talked about, but for simplicity's sake of developing a mathematical relationship or an equation, let us say that we are going to determine a transit stop locations to satisfy just the single objective of minimizing the passenger travel time. Only one objective, right. So, that is the only to minimize the passenger travel time, and we are not considering any of these for the moment, right, for simplicity's sake. So, we already know that passenger travel time on a transit line consists of two components: the access time, which includes the wait time at the station, and also the actual travel time on the transit line. So, now in order to develop or in order to know where the station should be located, two trade-offs have to be made. One is a trade-off between area coverage and operating speed, and we will see what that is, and also a trade-off between local passengers and through passengers, right. These two trade-offs will determine where you should locate your stations. Okay. So, let us look at each of those trade-offs. So, area coverage versus operating speed, right. So, if you think of a transit line, okay, and you want to put your station locations here, here, here and here. So, for example, this station location is going to cover, say for example, this much area, whereas this station location is going to cover this much area. That depends upon, so the area coverage depends upon how dense the population is, do you have enough street network there, do you have enough feeder routes. So, all of those determines the coverage area of a transit line. So, in this case what is happening is now this much of an area is getting neglected, right. So, if anyone of you live here or have their offices there, they are not well catered to access any of these two stations, because now it will be too far away from them, hence they would not get on the public transportation line, and then they may just take their own private transportation. So, that is the area coverage determination. So, how much area should a metro station cover, right? That is one determinant. The other is operating speed. The operating speed is the speed of the transit vehicle in itself. Okay. So, what is the trade-off that is being made here? If you increase the density of the stations, so now in order to increase this area coverage, if you say you increase the density, that means density of station means number of stations per kilometer, right. So, in order to increase the density, maybe you put another station here, right, in the center, you put another station right in the center. Now, what happens is you have overlapping area coverage, which is now redundant. Now this much area becomes redundant, however, you increase the coverage. But what happens with the increase in coverage? It decreases the access time, which is good. So, now people living here, they can quickly go here, whereas the access time to these locations from those locations to those stations were large. So, it is doing one good, but it increases the travel time on the transit line. Now, what happens is there is suddenly another station here. So, this say a BRTS or a metro line now has to, once it starts from this station, it has to again stop here. So, there will be some lost time, deceleration time, again it has to accelerate, again it has to stop here. So, lost time, deceleration time. So, now instead of it starting here from point A to point B, where it could have nicely accelerated and gone here, it has to now make a pit stop here at C, where it is adding to a lost time. So, what is happening is while making a trade off between area coverage and increasing the density of stations, the actual speed of the transit line is going down. So, how do you make that trade off so that there is a balance? So, there is enough coverage and also good speed or good travel time on the transit line. That is the first trade off that is made when you are trying to determine a location of a transit stop using this method, right. Using this method, meaning it is only fulfilling one of the objectives, which is to minimize the total passenger travel time. The second trade off that is being made here is between local and through passengers. Now, if you consider a transit line and you are getting up on A and you want to get down at C, right, but there is a intermediate station here called B, where you at this station you are a through passenger, right. You have already boarded the transit line and it does not matter to you whether this location or whether this transit stop is there or not, because you want to get down at C. So, at this location you are a through passenger, whereas there are many people who want to maybe board at that station. So, for those people they are local passengers at that station, right. They want the train to stop there, whereas you who is on board the transit line is a through passenger and you do not want the train to stop there, because stopping of a train means, for example, again increase in lost time, increase in the travel time on the line. So, you may rather want the station train to go quickly to your destination to point C, you do not want to stop. So, how do you balance this? Now, you also want people to get on there, but you also want the travel time to be not reduced for people who are already on board. So, station spacing then becomes a function of number of passengers with origin destination within the section divided by the number of passengers who want to pass through the section, right. So, if your origin and destination falls within the section, you are a local passenger, whereas if your origin and destination do not fall within that section, then you are a through passenger for that section. So, the greater the ratio, the more closely the station should be. So, if there are more number of local passengers, that means more people want to board and disembark in that section, then what you have to do is you have to have the stations more closely spaced together. If you think in your mind, when does this situation arise? Maybe in a central business district, right. A central business district may have 3 or 4 stations, which is only a section of the entire line, but within that section many people want to board and alight the transit line at each of those 3 or 4 stations. So, there are a lot of local passengers, whereas there are very few through passengers who want to actually go and not want to get on and off at a CBD. So, in those cases, so in CBD you will see the station spacing very close to each other, whereas if the ratio is the opposite, then you will have spacings which are far away from each other, which happens when you are at a suburban location, for example. So, suburban locations, the density is too less, people usually do not want to board on and off at too many locations. So, you will see that the spacing is different, right. So, if the volume of through passengers dominate the local passengers, station should be spaced at a longer distance, that is just the reverse of this. So, these two trade offs are kept in mind when you are developing the station spacings using this method. Okay. Now, let us go ahead and see how this mathematical relationship is developed. I am going to show you the entire derivation of the formula, but you most likely have to use only the formula at the end, but understanding the derivation will tell you, will make it easier on you to realize the concept of this, of how to determine the spacing. So, if you consider a transit line of length L, right, which has n plus 1 stations, and distance between any 2 stations, say k and k plus 1. Okay. The distance, the spacing between them is S k, and if the spacing is equal over the entire length L, then S is L divided by n. So, if you think of these are all equally spaced, then each spacing is L divided by n, and assume that the passengers go to the nearest station. That is a safe assumption to make, right. You would not want to access a station which is farther away from another station. So, say for example, you are living somewhere here and this and your direction of travel is this way, right. Your direction of travel, you want to access the station that is closest to you, either k or k plus 1, whichever is closest to you, you want to access that location. So, that is an assumption that we make in developing the relationship. Okay. So, clear enough, there are 2 stations. If you consider k as the boarding station and m as the alighting station. So, what we want to develop is the spacing between them. If you know the spacing between them, then we can tell where to exactly locate them, right. So, spacing between 2 will determine the location on where it should be, location of where it should be placed in a transit line. So, now what we need to do in the first step is to determine the market shed of passenger choice, or which is called a passenger shed area. What happens, what is a passenger shed area is, you see this line here demarcating the spacing between the 2 stations k and k plus 1 by what is called a g k and an h k, right. So, it is this line is demarcating the spacing into 2. Now, what is usually what happens, usually what the thinking is that the market shed should be half and half, right. That line should be right in between the 2 stations. The market shed or that line, whatever it means, is that if you are staying anywhere here or here, in the midpoint between two stations. Say this is the midpoint between two stations, and say we assume that that is the market shed, right. We assume that that is the market shed. However, we will see how the market shed has shifted to that side. If you were staying on this midpoint line and your direction of travel is here. So, you want to board at one of these two stations k or k plus 1 and want to travel to m or m plus 1. What would you intuitively do? Although you are right in the middle of those two sections, two stations, where you may want your distance travel time to this and this may be equal, but what you would want to do intuitively is you would want to travel to the station that is in the direction of travel, right. Although these two travel times T1 and T2 may be equal, but you would want to travel, you would want to travel to k plus 1, because if you went to k, then again you have to get on the transit line. So, there will be this travel time and this T3 that will be added on to your total travel time, right. Rather than that, you would just want to go to k plus 1 and then get on the transit line. So, what is happening is, even though you are in the center of the market shed or the passenger shed area, you are more and more likely to go towards the station that is towards the direction of your travel. So, what is happening is the area, the shed area is increasing for you. So, this area which is I am not saying area, but I am saying in terms of length. If you consider the perpendicular distances to be equal, so we can say the area in terms of the length hk. So, this hk is becoming greater and greater, right. So, more number of people who are in the center and a little bit off center are all going towards k plus 1 and not going towards k, because k is in the opposite direction of travel. Hence, this market shed area is shifting towards the left, or is shifting toward in the opposite direction of travel, right. So, just the opposite happens at the alighting station. At the alighting station, if you think of which station you want to get off, depending upon where your final destination is, right. So, if you have already these are the two stations, right, these are the two stations. If your destination is here, right, would you want to get off, your train is coming from here, would you want to get off at this station and then travel back, or would you have rather got off at the earlier station and traveled to this location, right. That is the trade off you are making. Now, it is just the opposite, you want to get off at the earlier station and then walk towards your final destination, rather than get off at the later station and walk back to your destination, right. So, that determines the market shed line. Okay. So, that is what is called the market shed area or the market shed line. Now, if you remember that concept now, what is happening is the access time to the station located in the direction of travel, right, in the k plus 1 is equal to the access time located in the opposite direction plus the travel time on the transit between the two stations, right. As I said, you would rather take T2, right, T2 rather than taking T1 plus T3. So, this T3 which is the interval between passengers arrival at the station and departure of the travel time, which is the wait time at the previous transit stop. So, if hk, again hk is this, hk divided by Va, Va is the access or the speed of the access to the station. So, say you are walking to the station, so your speed will be something. If you are bicycling to the station, your speed will be something else. So, that is called access speed. So, that is time. So, distance by speed, time, plus if you add Tw, which is again you have to wait at that station for the train to arrive as well, is equal to, now if you had gone to Gk, right, if you had traveled this distance and gone back to the station in the opposite direction of travel, again some speed you would have gone at, but there would have been this element Tk, which is the travel time of the MRT or the mass rapid transit on the spacing Sk, right. So, it would have been, again you have to travel this extra distance now, because you have gone back to a transit line. So, these two, when you equate these two, what you start seeing is that we already know Sk is equal to Hgk plus Hk, and if you substituting in the earlier equation, if you substitute this in this equation, you can cut those two. What you will get is Gk in terms of spacing and Hk in terms of spacing, and also you already know what is your access speed and what is the speed on the MRT line, right. So, now you have got your market shed or your passenger shed areas in terms of spacing between the two stations. Now, moving ahead, if the station spacing is sufficient, then the train can reach its maximum speed. Remember, one of the trade offs we are making is coverage area versus speed, right. So, if the spacing between the two stations say is sufficient, what that will allow is the train to pick up, accelerate, a train or bus to accelerate and reach its maximum speed, right. It can reach its maximum speed. So, if Tk is the time taken to travel between the spacing Sk with V as the speed, but there is always a TL associated with it, which is time lost for stopping at one station. So, if you write Tk again in terms of Sk, in terms of spacing, and substitute this equation in the previous equation, in these two equations, what we get is Gk in terms of Sk, right, V, Va by V, Va is access and V is speed of on the transit line, travel time lost and access speed. So, we are only getting it in terms of Sk, and then if we convert all of this into some constants, say we say Va by V is rho, right, this is equal to rho, and then we say alpha is 1 by 2 into 1 minus rho. So, this is 1 minus rho and this is 1 by 2. So, if we say that is alpha, and beta is 1 by 2 plus 1 by rho, 1 by 2 into 1 plus rho, and gamma, and if we convert this TLVA by 2 term into gamma. Okay. So, if you just simplify this equation by converting these into some constants, what we get is your passenger shed areas in terms of spacing, and all the other terms are constant, right. So, what this tells you is Gk and Hk. Gk, again remember, Gk and Hk, these are the market shed lines or passenger shed lines that we are trying to determine, which will allow you to know the spacing between two stations. Now, if what this tells you is Gk and Hk are governed by alpha, right, alpha or beta, right, it governed by alpha or beta, and which alpha or beta are again governed by rho, and rho is nothing but Va by V. So, what this is telling you is when Va by V becomes very less, right, becomes very less, meaning this is too high and this is too low. That means the MRTS, so the metro line, the speed on the metro line is very larger, much larger than the access speeds to the metro line. That means access speed, meaning everybody is walking, whereas the metro is going at 60 kilometers per hour, whereas your walking speed is maybe 4 meter per second, 5 meter per second, whatever it is. So, at that point the market shed line comes to the center, right, then Gk and Hk becomes equal. Whereas, if your access speed increases, if this now starts increasing and this comes very closer to 1, then what happens is the market shed line starts moving towards the station in the opposite direction. Then the station in the direction of travel gets a lot of people accessing that station, and the previous station becomes almost redundant. Nobody is taking that station. So, that is the time when you can remove that station, right. So, if the access speed increases, that is why people want more feeder buses or feeder systems, auto rickshaws to provide access. So, that will increase the speed of the people accessing the station, and by that you can almost sometimes remove a station on a transit line, which will then increase the travel time or increase the speed, reduce the travel time on the line. Okay. If you understand that, now that we know the spacing between, or we know the market passenger shed line, if you assume uniform passenger distribution, that is boarding and alighting are uniform, spacing of uniform along the spacing of transit stops for the entire line, then you can determine you can determine the GK and HK as a function of total passenger travel time, because that is what, remember, the objective that we are trying to solve is minimizing the total passenger travel time. That is the objective, and hence we want to know how to space the stations. Now we know the passenger shed lines in terms of spacing. Now we want to know the spacing in terms of minimizing the passenger travel time. So, if you again we are now assuming uniform passenger distribution. That is a very unrealistic assumption to make, because you will never have uniform passenger distribution throughout your transit line, right. You will not have the same number of people boarding and alighting at every stop. But again, to make it simplistic, for this mathematical expression to be developed, we are assuming that kind of a uniform passenger distribution. So, for uniform boarding, if there is a function B of S is equal to B, and uniform alighting A of S is equal to A, so then all are equal, right. So, if you assume that, and as boarding and alighting are uniform, ratio of passengers on a train to those along the line is constant. So, ratio of passengers on train to those along the line as in along the line waiting on the platforms are almost constant, and optimal station spacing must be uniform. So, the station spacing must be uniform. We are trying to calculate the station spacing, but in this case whatever station spacing we calculate would be uniform throughout the line. So, that is a very oversimplistic way of developing it, but at least you understand what are the elements in developing this spacing of the station. Okay. Now, the total passenger travel time, as you know, consists of two parts, access time and the travel time on the line. So, that has to be now developed in terms of spacing. Okay. So, let us go ahead and look how that is done. So, if the boarding density is B, already we looked at passengers per kilometer, and there are G number of boarding sections, we looked at GK and HK, right. So, remember consider there are G number of such boarding sections. So, total boarding would be G times B, and the average access time for the boarding of passengers, access time we already know G by VA. So, if you could say it is an average, so we just divided by 2 G by VA. So, now the total passenger access time. Okay. So, passenger access time for all the passengers who want to board or alight, right. Access also includes your egress time essentially. So, it also includes the time that will take you to reach your destination from the station where you disembark from the metro line or bus line. So, if you already know that this many people are boarding, right, from G stations, there will be then that many people also boarding from H sections, right, and you already know the average access speed for those sections. You multiply it by 2, because just like I said, you also have another set of M sections, M and M plus 1, where you alight. So, the similar thing is going to happen there. So, you multiply it by 2, and there are n such sections. So, you multiply that by n, and then there will be the waiting time for at each of those, the entire length of the section L. So, all these people have to wait for a certain amount of time, T w. So, that time plus the access time comprises of P T A. Okay. So, now we know P T A, and again if you substitute those old constants that we had already developed previously into this equation, what you will get here is P T in terms of spacing again, right. Remember, we have to P T A in terms of spacing. So, we have to convert everything in terms of spacing, and so that we are eventually looking to space the stations, or we are eventually looking to space where or space the stations along the transit line or along the metro line, right. So, now again by converting by replacing many of those terms here, you through those constants that we had developed, you would get P T A is equal to L times B times L A into 1 by V plus TL by S. So, all of these are simple terms to remember, simple terms to understand. And the other travel time that we now have to calculate is the travel time along the transit line, right. Access time plus travel time along the transit line. Now, travel time along the transit line will be, if the total passengers boarding along a transit line L per unit time is L times B, average length of travel for each passenger. So, each passenger will not travel the entire section of the transit line, right. They may be only traveling a part of that length of the transit line. So, if you consider average to be L A, then every passenger passes L A by S station spacing. So, if you consider different station spacings, so they will cross only L A by S station spacings, and they will not travel the entire spacing of the transit line of the stations. And if the average speed on the transit line is V for given spacing, then the passenger travel time on the transit line equals L times B, L A by S, it is only going to L times B times L A by S plus multiplied the whole thing by speed by velocity, whatever spacing by velocity, right. For whatever given spacing, what is the speed, plus TL. TL is the, remember, the lost time, the transit line has to stop and restart every time there is a station. So, lost time. So, if you use this term, then what you get is the passenger travel time on the transit line as L times B into L A times 1 by V plus TL by S. So, now if you add both of those terms, since PT is equal to PTA plus PTT, you add those two terms, you get this, and eventually what you have to do is, since you have to minimize the travel time, you have to, if you just do a derivative of PT with respect to S, right, you do a derivative of PT with respect to S and equate it to 0, what you are going to get is S is in terms of rho and gamma, and rho and gamma, as you already have seen, rho and gamma are in terms of let us see where the we had developed gamma, rho and gamma are in terms of TLVA. So, you already know all these values, what is the lost time, what is the access speed, and so on and so forth. So, now we have developed the spacing between stations in terms of certain metrics that you can calculate on the field. If you calculate those metrics, you can determine the spacing. However, you can see that the magnitude of the spacing is what you can estimate using this equation, right, not the exact spacing, because remember we had so many assumptions that we had to put in there, and beginning of the problem what we said was this was only solving one objective, not all the other objectives. So, this is a very simplistic view of understanding the spacing between two stations. However, it gives you, that is why the magnitude of the spacing and not maybe the exact distance between two stations, but it gives you the magnitude of the spacing. So, what it tells you that the magnitude of the spacing is it will be higher if people travel longer distances. LA is the distance traveled by each person, right. So, if people travel longer distances, the spacing should be longer. Gamma, again gamma is TL into VA by 2. So, if the losses times are greater, then the spacing is greater, right. If the access speed is greater, the spacing can be greater. So, it gives you a relationship between different parameters that you can measure on the field, and it gives you a value of or a magnitude of spacing between the two stations. Okay. I hope you have followed through the derivation part. Eventually, maybe you will only need to use maybe this formula or this formula to calculate what is the magnitude of spacing, but once you understand the derivation of it, it helps you in understanding in real life situations how do you develop the spacing between the stations on your mass rapid transit line. Okay. So, I hope you have followed through whatever we have explained to you today. Basically, what we have done is explain the bus stop location determination, and sorry, this slide is mixed up, but again all of this is taken from from the textbook of Vucic, and you have access to it. There is another textbook which is an Indian textbook, which also tells you to solve some problems in understanding the spacing of transit stations along a mass rapid transit line. Thank you very much for your attention.